When you think about progress in AI, you probably picture a straight line, right? More data, bigger computers, you get smarter models. But what if I told you that sometimes the biggest leaps forward, the breakthroughs that change everything, come from ideas that seem, well, completely backwards? Today, we're going to dive into two amazing stories where the path to a smarter AI was paved with some seriously counterintuitive thinking. So let's just start with the most basic question. You've got an AI that can recognize images, and you want to make it better. What's your first move? The logical approach would be to just make its brain bigger, right? Make the neural network deeper, add more layers so it can learn more complicated stuff. But what if the real answer was to show it images that were specifically designed to fool it? One of those sounds like building a better engine. The other sounds a lot like sabotage. Well, as we're about to see, both of these weird, paradoxical ideas led to absolutely massive breakthroughs. Let's kick things off with the very strange case of the network that got too deep for its own good. Okay, so picture this. It's the mid-2010s, and everyone in AI is chanting the same mantra: deeper is better. But as they followed that logic, they slammed right into a wall, a really bizarre problem that just didn't make any sense at the time. The whole idea behind deep learning was that more depth equals more power. But as researchers built these towering networks, something weird happened. It was almost like a game of telephone. The message, the signal, it was getting all garbled passing through so many layers. And the networks weren't just failing to get better, they were actually getting worse. And this graph shows you the problem perfectly. On the left, you've got a 20-layer network. Its error rate is pretty low, not bad. But now look at the 56-layer network on the right. It's way deeper, it should be smarter, but its error rate is actually much higher. The AI was literally getting dumber as its brain got bigger. And don't just take my word for it. This wasn't some fluke. The researchers behind the famous ResNet paper documented it plain as day. They called it the degradation problem, and it basically meant that the whole strategy of just stacking on more and more layers was a dead end. So, what do? How do you solve a problem where adding more power just makes things worse? Well, the solution was just breathtakingly elegant. It all came down to creating a kind of express lane for information to travel through the network. This little diagram here shows the genius idea in action. It's called a residual block. Now look closely. The input, that X, it goes through the normal processing layers like always, but it also gets to take this shortcut connection that completely bypasses them. It just zips around the side. Then, at the very end, the original untouched input is simply added back to whatever the layers came up with. So here's the magic trick. If adding a new layer doesn't actually help, if the best thing it can do is just pass the information along unchanged, it doesn't have to struggle to figure that out. It can just learn to make its own output 0, and that shortcut takes care of the rest. It made it ridiculously easy for a layer to learn how to do absolutely nothing. And that, paradoxically, was the key to everything. And just like that, this simple idea completely fixed the degradation problem. All of a sudden, researchers could build networks that were hundreds, even thousands of layers deep, and every single layer could actually make the model better. It was a total game changer. Okay, on to our second paradox. This one isn't about how the network is built, but about what we feed it. What if the best way to make an AI stronger is to attack it? All right, have a look here. On the left, we've got a picture of a bird, and a standard AI has no problem seeing it as a goldfinch. Easy peasy. Now look at the picture on the right. To you and me, it looks almost exactly the same, right? Maybe a little bit of static. But to that same AI, that image is not a goldfinch. No way. It might think it's a starfish or a school bus. This is what's called an adversarial example. So these aren't just random corrupted pictures. They're meticulously crafted. Someone has added a layer of digital noise that's basically invisible to us, but it's designed with one purpose: to trick the AI. For a long time, everybody saw these as a catastrophic failure, a huge security flaw that just proved AI vision was brittle and easy to fool. I mean, it's pretty scary, right? This massive vulnerability. But then, a group of researchers at Google asked this brilliant, totally counterintuitive question. What if we could harness this? What if training an AI on these trick images could actually make it better at seeing normal images? The key insight they had was this. Adversarial examples aren't just messed up versions of normal images. They are fundamentally different. They follow different rules. Just mixing them in with your normal training data is like trying to teach someone English and Klingon at the same time by just jumbling all the words together.
It's just going to create confusion. You have to treat them separately. And this diagram shows their solution perfectly. On the left, that's the old way. You throw the clean images and the trick images into the same pot, and the model gets confused. But on the right, that's their solution, called adverb prop. They created a totally separate processing lane just for the adversarial examples. It's like giving the tricky images their own private tutor who knows exactly how they work so they don't mess up the main lesson.
So did all this backwards thinking actually work? I mean, letting networks do nothing and training them on their biggest weakness, did it pay off? Well, the results really do speak for themselves.
The results were pretty amazing. I mean, sure, AdProp gave a nice little boost on the standard benchmark test, but that's not the real story. The real breakthrough was on the harder tests. On ImageNet A, which is a collection of really tricky, real-world images that other models get wrong, accuracy jumped by a whopping 7%. That means the model wasn't just better at passing a test, it was genuinely more robust and reliable out in the wild.
And when they applied this technique to an even bigger model, they hit this number: 85.5% top 1 accuracy on ImageNet. That set a brand new state-of-the-art record. And the craziest part? They didn't do it by getting billions more clean pictures. They did it by strategically using the very trick images that everyone used to think of as a critical failure. So there you have it, 2 beautiful examples of progress through paradox. With ResNet, we learned that making it easy for a component to do nothing was the key to unlocking unbelievable power. And with AdProp, we found out that a model's greatest weakness could be turned into its greatest strength. It just proves that sometimes the biggest leap forward comes from just looking at the problem in a completely new way.
And that kind of leaves us with a fascinating final thought. We tend to look at an AI's mistakes and its flaws as things that we just need to patch up and fix. But what these stories show us is that sometimes they're actually clues. It really makes you wonder, what other quirks that we all see as bugs today are actually the keys to the next big breakthrough?